In this video, we're going to start our exploration or our study of specific types of functions. And in this specific video, we're going to talk about quadratic functions. And then we're going to switch gears and we're going to start talking about quadratic inequalities, which are inequalities that involve quadratic functions or expressions. So we've already discussed or talked about quadratic functions before. But remember, a quadratic function is a polynomial function that can be written in the form ax squared plus bx plus c, where a does not equal 0. Because if a equals 0, we wouldn't have that x squared term, and we'd have a linear function. All right, now b and c can both be 0. As long as we have a squared term, this is called a quadratic function. There is another way that we could write a quadratic function. Is f of x equals a times the quantity x minus h squared plus k. This is the type of quadratic function that we've seen when we were dealing with transformations of functions. And so what we're going to do is we're going to review the graphing of a quadratic function like that so that we can identify some properties of the graphs of quadratic functions. And so here in this first example, we have f of x equals negative x minus 4 squared plus 1. We want to graph this quadratic function using transformations. And so the first thing I'm going to do is I'm going to identify all of the transformations. Well, what we have to do is we start with our most basic function, meaning remove the negative, remove the minus 4, and remove the plus 1, and we'll see that we have our squaring function. So that's my function that I'm going to start with. Then my first transformation is the first thing that I can see that's done to that x, and that's the minus 4. So I'm going to graph next y equals x minus 4 quantity squared. That means I'm going to shift to the right 4 units. Then I'm going to graph the negative that's out front. So that's the next operation I'm going to look at that's completed. And this means to reflect about the x-axis. And then last but not least, I'm going to graph on my picture to the right, on my coordinate plane to the right, the plus 1. And that just means that I shift up 1 unit. And so I'm going to go ahead and start. I'm going to try to do these transformations using these colors here. And so y equals x squared, I'm going to remember that I'm going to plot at least 3 points. And as we could remember, we have a parabola that looks something like this. All right, it's not drawn to scale or whatever. As long as it goes through those points, I'm happy, right? And so I have my first parent function. Now I'm going to transform this by moving all of my points to the right 4 units. So where I had the point negative 1, 1 is going to become the point 3, 1. Where I had the point 0, 0, move that to the right 4 units. I'm going to have the point 4, 0. And then my last point that I had was going to be the point 5, 1. And I have my second graph. Ooh, it's hard for me to draw on the screen. I'm sorry. So that's y equals x minus 4 quantity squared. And then I'm going to go ahead and I'm going to graph y equals, that's the equal symbol here, the negative x minus 4 squared. That means I reflect about the x-axis. And so the point where I have 3, 1 is going to be 3, negative 1. The point 4, 0 stays the point 4, 0 because 0 is a neutral number. So if I'm trying to multiply 0 by a negative number, it's going to stay the same. And if I multiply this 1 by a negative 1, I'm going to get the point 5, negative 1. And so I get a picture that looks something like that. And so I have y equals negative x minus 4 squared. And my last step in my transformation is to shift everything up 1 unit. And that's going to be my final graph here. And so the point negative 3, 1, negative 1 becomes, 3, negative 1 becomes 3, 0 when I shift up 1 unit. The point 4, 0 becomes the point 4, 1. And the point 5, negative 1 becomes the point 5, 1. And we'll have our function that looks like that, right? You can always check that your final graph is the correct graph by plugging in some points. For instance, if I plug in the point 3 in for x into my final function, 3 minus 4 is -1, but when I square that, I would get a +1. But it's multiplied by a negative here, so I get -1. Add 1 to that, I get 0, right? And you can do that for these other points here. So we've done these transformations here. Now let's see some properties. For instance, one of the properties that I noticed is that I have a highest point, right? This point is your vertex. It's at the center of your, or right in the middle of your parabola. In this case, it is a maximum point, okay, because that's the highest point. It sets the largest y value that your function passes through. And that vertex is actually coming, when I see my function written this way, it's actually coming from this 4 here and that +1, right? So that vertex is actually that HK, which you see there, right? That's one property we want to discover. Another property is that if I think about that vertical line that passes through my vertex, it actually kind of separates or divides my function in half. That vertical line has an equation of x equals, and it's the x value that all of these points on that vertical line has, 4. This line is actually a line of symmetry because it divides our parabola in half, and so we call this the axis of symmetry. And it is that same value 4 that is the x coordinate to our vertex, and so the line x equals h is our axis of symmetry. All right. This parabola opens downward. Now, when we were looking at the transformational steps, this first one here and this one here open upward because notice there's a positive term as your leading coefficient here, and there will be a positive term as your leading coefficient here. But once we have that negative, it made it open downward, right? And so that value that's in front of that x squared is very important too, because it's going to tell us whether our parabola opens upward or downward, because it's going to represent either a reflection or not a reflection of our squaring function. And so let's summarize some of these properties here. When our parabola is written in this form right here, a, which is that leading term, is going to be your leading coefficient. It's going to be an indicator of how your parabola opens. When a is greater than 0, it opens upward, which was the case in y equals x squared and y equals x minus 4 squared. That there's a +1 and a +1 as in the space of your a in this formula here. And when it's negative, it's opening downward. Your vertex is given by the ordered pair HK, as we said before. The line x equals h is called your axis of symmetry. And so we can use these things in addition to finding our intercepts to help us graph a parabola. And so what we want to do is we want to develop a method so that we won't have to go through these transformations every single time in order for us to graph a parabola. And so let's look at an example where we do that. It says identify the vertex, axis of symmetry, intercepts, and opening of the parabola given by f of x equals 3x squared plus 6x minus 1, then graph and state the domain and range, right? Well, we know that our vertex is given by the formula hk. Our axis of symmetry is given by the line x equals h. We know how to find intercepts. To find your x-intercept, you substitute 0 in for y and solve for x, and you do the opposite to find your y-intercept, and we know how to determine how our parabola opens by looking at that value a. Now, remember, our parabola, when it's given in this form where our vertex is hk, our axis of symmetry is x equals h, is written in this form right here. And so when our parabola is not written in that form, we have some work to do to get it into that form. And the way we're going to do that is to go from having a polynomial that looks like that to a polynomial that looks like this, is to complete the square, all right? Now, completing the square gets a little difficult here. Remember when we completed the square, in order to get a perfect square trinomial, we had to have a 1 as our leading term, our leading coefficient. Right now, we have a 3. And so what we did before was we divided everything by 3. I'm not going to do that because I technically don't have an equation here. Now, in a sense, you really can do this. I'm not going to do it here. What I'm going to do is, instead of dividing by 3, I'm going to factor out the 3. And remember, when you complete the square, you complete the square on these two terms here. So I'm going to factor out a 3 from those two terms. I'm going to be left with an x squared plus 2x. And notice here, I'm not going to leave that factor out a 3 of that constant term, because the constant term can be consumed in this part right here. I only need to complete the square on the first two terms, okay? Now, when I factor out a 3, now when I look inside of my parentheses, I have a 1 in front of my x squared. So now I can do a b over 2 quantity squared. And my b is a 2. So that's a 1. So what I'm going to do is I'm going to write this polynomial as 3 times x squared plus 2x plus 1. Now, what I've done, and then I have my minus 1 there. What I've done is I've not added 1. This 1 is inside this parenthesis here. I actually have a distributive property, right? So that by adding a 1 inside this parenthesis, I'm actually adding a 3 times 1, okay? Because of my distributive property. And so since this is not an equation, right? I have to add it to both sides. Well, I'm thinking of function notation, and so I'm thinking of only having one side. Remember, if I add something, I have to subtract the same thing if I want to, end where I started with. So I'm adding 3 times 1. I'm also going to subtract a 3 times 1. We know that 3 times 1 is 3. That way, this equation is exactly the same as the equation that I started with, because I have to undo this adding by 3. When we were completing the square to solve quadratic equations, we added the same number to both sides. This is how we do it when we're using function notation. All right, so I have this here. Now I can factor this into x plus 1 times x plus 1. So this becomes a 3 times x plus 1 quantity squared. And we know that 3 times 1 is 3. So that's a minus 3. Minus 1 minus 3 is minus 4. All right, and so we have this. So I know my vertex is given by hk. H is the value that I'm subtracting from 1. When I see a plus sign, I'm subtracting a negative. So that's a negative 1. And whatever sign I have on my k here, I take that. So I have negative 1, negative 4. My axis of symmetry is the line x equals the x coordinate of my vertex, which is negative 1. Remember, it is an entire line, so I need to see x equals, all right? And then my opens, however, my parabola opens, since that 3 is positive, I know it opens upward. I have some information that I already know about this parabola here from when I graph it. I know negative 1, negative 4 is the vertex, and I know that the line that passes, the vertical line that passes through that is my axis of symmetry. All right. Now, I need some other points in order to help me graph. So I'm going to find my x-intercept. Now, you can go to this form right here to help you find your x-intercept. All right. That means you plug in 0 for x and you, for y are your output, and solve for x. I get 4. So 4/3 when we divide both sides by 3. We can take the square root of both sides. When I take the square root of both sides, I have to put on a plus or minus. That's 2 over the square root of 3 equals x plus 1. And so I get x equals negative 1 plus or minus. If I multiply the numerator and the denominator by the square root of 3, I get 2 square root of 3 over 3. Now, what number is that? Especially since we don't have a calculator, I don't know. So what I'm going to do is I'm going to find my y-intercept, and we're going to see that we really don't need to know the x-intercept in order for us to get a good graph. But we can get it with getting our y-intercept. So with our y-intercept, we plug in 0 for x. And so we get 3 times 1, because 0 plus 1 and then squared is 1. And so we get negative 1. So that's the point 0, negative 1. I can plot that point here. And if I told you that you had a graph with 3 points, well, since I know my y-intercept and it's 1 unit from my axis of symmetry on the right side, by the logic of having a line of symmetry, I know that my graph goes through the point negative 2, negative 1 as well. And so I have 3 points. Now I can plot my graph my polynomial function, my parabola. and I get something that looks like that. Now, this is not a V. I try to make it a U-ish shape, but I have that right there. My domain, all real numbers, and my range from lowest to highest. My lowest point is this point here, has a y value of -4, and it continues forever upward to infinity. Okay. Notice here, my vertex here, well, here, my vertex is a maximum. So when I'm, a minimum, that is definitely not right. So when my parabola opens upward, we have a minimum, and like in the example above, when my parabola opens downward, we have a maximum. All right. And so now what we know is that we can easily find the vertex of a parabola. Now that we can do that, we can also find the maximum and the minimum values of your quadratic functions. All right. Now, what we've done was we've used the properties of a quadratic function that's written in this form right here. The vertex is given by HK. All right. Well, when I have a parabola that's written in this form right here, I'm going to do this really quickly. If you don't fully understand this, it'll be okay. But I do want you to understand this. All right. If I were to try to write f of x equals ax squared plus bx plus c in this form here, right? Then in order for me to find my vertex, which is hk, I would have to complete the square. Well, if I complete the square, I would have to factor out the a here so I can get a 1 in front of my x squared. So I have to factor out an a out of these first two terms. When I factor it here, I'm left with an x squared. When I factor it here, I get b over a times x. Notice I'm not factoring it out of the term c. Now with that, remember, we always use b over 2's quantity squared in order to add it to complete the square, right? So in the place of b is this whole thing here. I have to do b over a divided by 2 squared. When we divide by 2, we multiply by the reciprocal of 2, which is 1/2. So b over a times 1 over 2 is b over 2a quantity squared, which is b squared over 4a squared. So that is what I'm going to add right here, right? So I'm going to have f of x equals a times the quantity x squared plus b over a times x plus b squared over 4a squared plus c. And remember this, when you add this, you multiply that by a actually. So what I'm adding here is a b squared over 4a. So I have to subtract a b squared over 4a. Now, notice that was an a squared, but it cancels with this a when I multiply. So what I'm adding right there is a b squared over 4a. So that's why I'm subtracting a b squared over 4a in order to complete the square. All right. And this is going to equal a times, I will factor this, x plus, and remember, whatever you square here is a hint of what you're going to write here. So since that's b over 2a squared, and then plus c minus b squared over 4a. And so my vertex is hk. Remember, your h is whatever you're subtracting from x. When you don't see a subtraction, you're subtracting a negative. So that's a negative b over 2a. And then my vertex has a y value, which is this term here, which is b squared over 4a. Now, a lot of times you will see people say, oh, your vertex has an x coordinate of negative b over 2a. And since, oh, I forgot the c here, that should be a c minus, because this whole thing is your y coordinate. Because this is a hard formula to remember, people say, oh, you can just plug in that negative b over 2a into your function, and that's going to give you the y value instead of memorizing this thing here. All right. And so if you wanted a formula for the vertex when your parabola is written in this form, then you get negative b over 2a, comma, and then f of negative b over 2a. All right, let's look at this example. I'm going to set it up and give you the solution, but I want you to work through it. All right. It says Kim wants to construct rectangular pens for 4 animals with 600 feet of fencing. To get 4 separate pins, she will fence a large rectangle and then fence through the middle of the rectangle parallel to the length and parallel to the width. What overall dimensions will maximize the total area of the pin, right? So a picture is worth 1,000 words. And actually, let me see if this, oh yes, look at this. So I have this here, and that's a rectangular pin. You're gonna make 4 pins. So I'm gonna have a one side length here, and then I'm going to have a side parallel to my width like that, and I'm going to get a figure that looks like this, right? And so if I want to find the dimensions, that means the length and the width, well, I know that this side over here could be considered the length, and then this side over here could be considered the width. Now we're given the fact that she uses 600 feet of fencing. That means this side plus that side plus that side plus that side plus this middle, and then that middle should equal 600, right? Well, my length is actually given 3 times, right? So I have 3 times my length, L plus L plus L, and the same thing with my width. I'm given the width 3 times in order to create this fencing. So W plus W plus W is 3W. That should equal 600. And so we want to find the overall dimensions that will maximize the total area. So we see the word maximum, which is very important, and we see the total area. Well, the total area is this area plus that area plus that area plus that area, which all together is the area of the entire big overall rectangle, which is just length times width, right? And so what we want to do is we want to write this equation in terms of one variable so that we have a function in terms of one variable. So what we'll do is we'll use this formula, solve for one of the variables. I'm going to solve for L. So I'm going to subtract 3W from both sides. And I'm going to divide both sides by 3. And if I divide 600 by 3, I get 200. 3 divided by 3 is 1, so I get 200 minus W. And so my area formula, which I want to maximize, is going to be given by 200 minus W times W. I can use my distributive property, 200W minus W squared. And if you want to write it like in the general convention of how we write parabolas or polynomial functions, I have a parabola that looks like that. And I want to find the width and the length that maximize this area function. And notice here, this is a parabola. My A is a negative, and I can figure that out. All right. So you can use either, you can complete the square and write it this way and use HK, or you can use this formula here and you find negative B over 2A. You know what? Let's go ahead and do it. So since my W equals I have my function equals negative W squared plus 200W. My B is 200. And my A is negative 1. That means my width is going to be 100, right? Negative 200 divided by negative 2 is 100. And if I want to find my length, I plug it into my formula here. So I get 200 minus 100, which is 100. And so my maximized area, the overall dimensions that maximize my area, this will be feet, this will be feet, 100 feet by 100 feet. Okay. Now let's talk about quadratic inequalities. These are inequalities that involve a quadratic polynomial, right? So inequalities, instead of having equal signs, they have a less than or greater than, or you can have a less than or equal to, or a greater than or equal to. So we're saying that something is less than or greater than, or less than or equal to, or greater than or equal to something else. There are multiple methods that we can use to solve quadratic inequalities, right? But what we're going to focus on is the test point method. So with the test point method, usually it's pretty simple, or it's simplest to compare things to 0, all right? And so what we're going to do is we're going to find all of our x-intercepts. When you have a polynomial function, if you think about a graph, of like a parabola. All right, so if this is f of x equals x minus 3 squared minus 4. These x-intercepts here are where your functional value equals 0, where your y value equals 0. So if I get everything on one side and solve the equation x minus 3 quantity squared minus 4 equals 0, then what I'm going to find here are points where my graph crosses my x-axis. These are your x-intercepts. Then what I'm going to do after I find my x-intercept, so we're going to select a test point in each interval created by the x-intercepts. A test point is any value that's in that interval. We're going to draw a number line and figure those out. Then we're going to evaluate the polynomial at each of the test points and see if we get a positive number or a negative number. If we get a positive number, then we know that our function has y values that are positive and is going to be above the x-axis. And if we get a negative number, then we know our function is going to be negative and below the x-axis. And then we're going to write our solution in interval notation. And so this first example here is x squared minus x minus 6 is less than or equal to 0. This is a perfect location to have your polynomial in, right? What we're going to do first is we're going to find the x-intercept of the polynomial function. So I got x squared minus x minus 6 on one side by itself and 0 on the other. If it weren't that case, I will get all my terms on one side and 0 on the other, right? What we're going to do is we're going to try to find the x-intercepts of this function here. That means we're going to plug in 0 for y, and solve for x. Well, this one can be factored. X minus 3 times x plus 2. Have two things that multiply to give me 0. We can set both of them equal to 0, and we'll see that x equals 3 or x equals negative 2. All right? These are our x-intercepts on a graph, for instance, right? This would be the x-intercept, right? And so what we're going to do here is I'm going to put those values on my number line. All right. Now, what we're interested in is this function being less than or equal to 0. This is a place where it equals 0, and this is where this function equals 0. So when I put them on a number line, I'm going to use a closed circle because it has an equal to. If it did not have an equal to, I'd use an open circle. All right. Now I'm going to use some test points. Test points are numbers that represent each of these intervals, right? For instance, this first interval involves the numbers between negative infinity and negative 2. I'm going to use as a test point the number negative 3. Okay? Between negative 2 and 3, a great test point is 0. I love plugging in 0 because it cancels things out. And between 3 and positive infinity, I'm going to use a number like 4. Now, you may want to use 5 or 10 or 100. Over here, you may want to use negative 5, negative 10, negative 100, right? I'm choosing these values here. These are my test points. So with the test points, I'm going to plug them back into my original inequality. Okay, so I have this inequality here. And this inequality is actually the exact same thing as this right here. Okay? And so what I could do is I can plug in negative 3 into this inequality. And the reason why I'm going here is because I don't have a calculator. And so this can allow me to quickly plug things in and see if I get a positive or negative result. For instance, this x minus 3, if I plug in negative 3 here, this first parenthesis is going to be a negative 6. Or it's going to be a negative value. That's all I care about. And the second parenthesis, if I plug in a negative 3, I'm going to get negative 3 plus 2 is negative 1. That's a negative. Well, a negative times a negative is actually a positive. So on this interval, I know I'm going to get a positive value. All right. Now I'm going to go back to this inequality, plug in this test point, which is 0. When I plug in 0, 0 minus 3 is a negative value. 0 plus 2 is a positive value, and we know that when we multiply a negative times a positive, we get a negative. So a negative value represents this inequality, this interval. Plug in 4, we get a positive times a positive in those parentheses, and positive times a positive is a positive. All right. And so what this is saying is that my function x squared minus x minus 6 is positive or above the x-axis. It crosses the x-axis at negative 2. It becomes negative or below the x-axis. until it gets to 3, where it crosses the x-axis and it becomes positive. So the graph actually looks like this graph that I did here. All right, that's what it would look like graphically. And that's after we got everything on one side and 0 on the other, which was given in the problem. Now, to solve this inequality, we got to give all the x values that make this expression here less than or equal to 0. Well, less than or equal to 0 means negative. And so my solution set, I'm going to focus on this closed circle here and these values on the interval where I have negative. So my solution is going to be the interval. Since I include -2, I'm going to put -2 and all the values until I get to 3. For instance, if I pick a number like 0, I can plug it in that inequality. 0 squared is 0 minus 0 minus 6 minus -6 is less than or equal to 0. But if I were to pick up a number like 4, 4 squared is 16, minus 4 minus 6 is 6. 6 is not less than or equal to 0. So that's why we focus in on this region right here. All right, so you can check your solution. Let's look at one more example. I have t squared plus 25 is greater than 6t. All right, well, when I look at this inequality, I want to get everything on one side and 0 on the other. So I'm going to subtract 6t from both sides. So now that I have that, our input variable is t here. I want to find the x-intercepts to this function here. I can't factor, so I've got to use another method. Remember, you always have your quadratic formula. So it's -b, so that'll be a positive 6, plus or minus the square root of b squared minus 4 times 1 times 25, all over 2 times a, which is 1. If I simplify this, that'd be 36 minus 100. And 36 minus 100 is -64. So that'll be a 6 plus or minus 8i over 2, or 3 plus or minus 4i, right? Notice these are imaginary numbers. These are not real. All right, when we solve this equation, what we did here was we set this equal to 0, right? To find your x-intercepts where it crosses the x-axis, you set your output equal to 0 and you solve for your input variable. What we got here was not a real number, right? So when we have not a real number, that means there are no x-intercepts. And so if my graph has no x-intercept, and I'm going to think about a function that looks like this. Remember that a, when we were graphing parabolas, was the leading coefficient? That is a positive number. That means my parabola is opening upward, right? So my parabola is opening upward and I have no x-intercepts. That means my function is completely above the x-axis. It's completely above the x-axis, all right? Because it won't touch it, but it's opening upward, so it can't. If it opened downward, it would have to go below the x. It would either be this way. Well, let's look at it. All right, it's going to be opening up upward this way and having no x-intercept, or it could open downward and have no x-intercept. The reason why I know it doesn't open downward is because my leading coefficient is positive, so it has to open upward. So it has to be completely above the x-axis. Okay. Now, with that being said, my goal is to find all of my real values that make this statement right here true. Where if I am looking for the input values that make my function t squared minus 6t plus 25 greater than 0, and my function is completely above the x-axis, then it works for every single value t. So my solution here is actually -infinity to infinity. I can plug in any number because I know I'm opening upward, I'm up completely above the x-axis because I have no x-intercepts, and so I'm done there. All right, this concludes that video. I'll see you next time.